It's been a very exciting day for me and also a very exciting week because some work I've been doing for the past 30 years has finally landed in C++. But the real work has been done by the people who are listed there, and I especially want to acknowledge Barry, Verfin, and Dan Katz, who have been spending all week long going through very meticulous words to try to figure out, and to try to figure out every little mistake that we might have made along the way. There's probably some left, but without them, I don't think we would have had reflection for at least another 2 cycles of the standard. So today I want to talk, well, I sent a title called Regularizing C++ for reflection to the organizer of this meeting, and thank you for inviting me here. But as I was thinking about it and preparing the slides, I realized I sent the wrong title. It's actually the other way. Reflection will be used to regularize C++. Right? And what do I mean with that? C++, it's a language with a long history, right? And it has accreted, so incrementally added a lot of things. It picked up some ideas from C, it picked up some ideas from earlier thinking in the 80s and the 90s. And so we have all kinds of notions, right? Things like variables, templates, types, namespaces, they're all very different, not always consistent. It also has all kinds of mechanisms, things like instantiation, overload resolution, initialization. And again, they're all irregular because you've probably seen the meme about initializing in C++, right? The Forrest Gump meme, there's lots and lots and lots of ways of doing that. There's a lot of rules, right? Like the rules about when you can access something, or when how overload resolution is done, how conversions happen, and those rules are full of special cases, right? We don't like special cases, but they're all over the place, and so on. So we need to now offer a view of the program as an API to the programmer, but we don't want all that irregularity. So what reflection can do is, instead of showing you the real language model, which is painful, we're going to present to the work we did a simplified language model. So wherever we can lie a little bit about the way the standard is specified without taking away features, we're going to do that. I'm going to show you some examples of that later on. The other thing that we decided early on, well, let me say it again, that we decided early on in this paper, in this project, is that we will use values to represent everything. Not only that, we'll choose values that are all of the same type. So whether you want to represent a namespace, or a function, or a type, or a template, or a base class relationship, and various other things, it'll be done with a single type, with values of a single type. And because it's a single type, you can treat those things in collections that are homogeneous, so efficient vectors, efficient hash tables, and so on. You won't have to deal with heterogeneous containers, which are difficult to work with, things like tuple and so on. We also ran into the fact that the language contains some mechanisms that are similar but oddly different. Right? I'll give you one example. C++ has pointers. C++ also has references. The rules for them are quite different. But you probably know that your compiler underneath it all just deals with addresses, right? And so if we were to model all the rules for these two things together, the complexity of your reflection programs would become, much larger. And so what we're doing is wherever possible, we're trying to treat those two similarly. I'll show some examples of that as well. And there's other examples. Now, when we talk about reflection, we didn't think only about, well, what can we do now? We're also looking at what's going to happen in the future. Right? And one of the things we've observed in the language is that every meeting of the C++ standard committee, when we're considering extensions, we get proposals that are very narrow. Right? Someone comes to the committee and says, I have this problem, and it's a real problem. It's something they cannot easily express in their programs. And so they say, well, I can't express it with functions, with templates, and so on. I need a special feature in the language, and because it's a special feature, I need a new syntax. And so usually we say no, because we don't want to accumulate 1,000 different kinds of syntax constructs for 1,000 different little things, but sometimes we say yes. Right? I'll show you one example of that hopefully later. it turns out that reflection provides us a new abstraction mechanism that allows us to do a lot of these things that people want to do in the language as library solutions instead. Now finally, there are some language features that we anticipate in the future, which really, even though they're core language features, or a new feature unrelated to reflection per se, it actually can make use of reflection. I'll mention one because I'm not going to have a separate slide on this. I'm not sure how familiar with C++ 20, but in C++ 20 we added the ability to have a template argument that is of a class type. Right? Like it's pretty common to put integers as a template argument. For example, stud array, you can say stud array of int, comma, 20. We've been able to do that since the first standard and even before. But since C+20, instead of saying 20, you could put a class tag there. But the kinds of class tags that can go there right now are very, very restricted. It's really limited. And these limitations are very hard to lift. And Regularizing and Faisal Vadi have figured out a way to actually release those constraints to allow many more classes, including something like string. Right? We really would like to be able to put a stud string as a template argument. And we think we can do it with the help of reflection. You wouldn't see it, you wouldn't see anything about reflection in there, but the protocol to make that possible across translation would use reflection. So I'm very excited. I think reflection is going to be sort of a change the perspective on C++ in the future. But we'll see if it works. P296 is a large paper. It's over 150 pages if you put it out in the normal fonts and so on. But I think I can explain pretty much all of the ideas in it in one slide. I exaggerate maybe as all of the ideas, but you'll get most of it in just one slide. Mostly, it's a long paper because it has to deal with a very large standard and formalize it. So what reflection is a way for the program to look at itself, right? So we have source code and we want to be able to look at it and programmatically deal with the concepts we've made. Like maybe we want to do something for every member of a certain class or print out email names or whatever it is. Right? I call it the syntactic domain. And I want to turn that into values. Right? One of the things we don't want is to represent every aspect of the text of your code. We want to represent entities. So we don't want to tell you how many spaces you put in the declaration of your function or how many function declarations you actually have. What we want to describe is, well, what's the type of the function, what are the properties of it. So, let me see here. Can you guys see stuff there? Yeah, this one. Okay. So we're introducing a new operator, which we call the reflection operator. Some people call it the kitty cat operator, the mountain operator. I've heard some other names. I call it the reflection operator. And you can apply it to a variety of things, right? You can apply it like stud vector int is a type. That second one here, that's still a type. It's a point to a function, taking the arguments and then no parameters and returning int. Stdcl is a variable. Stud vector is a template. Std is a namespace. Colon is sort of a namespace, global namespace. These other things you can represent functions, base classes, things like that. So now we have a way to get from a source construct a value. A value is always of type info, no matter what you're representing. This was a controversial decision. We've had it defended. It took actually years to convince the committee to go that way. But I think we made a really good decision there. The more we're progressing with use of that, we find it just was the right decision. So that type is actually a type alias for something the compiler knows internally. And you'll get that alias by including a header called meta. Along with the type, you get dozens, hundreds, well, not hundreds, but more than 100 functions to explore these meta values. Right? For example, say that you have your vec template, that's a bit like the vector, it takes a type, right? You can now ask the compiler for a handle of how it's represented. So now I have R of type stud meta info. I use auto just to be short. Okay. I can start exploring it with my meta function. There's a whole bunch of meta functions to ask reflections what they are, either broadly, like are you a template, but I could also ask are you a class template, or are you a const qualified type? Because any meta function that's currently in the standard has a counterpart as a const eval function. So this is a const eval function. I should also mention stud meta info is associated with namespace meta. So you can use this template without qualifying it. Argument-dependent lookup will find it. All right, so we know it's a template. I didn't actually have to test that. But then you have functions that allow you to synthesize more stuff. In particular, this function substitute is really interesting. You give it reflection of a template. You give it a range of reflections of template arguments, right? And remember, because there is only one info type, you can represent any template argument list. And then you get back a reflection for the specialization. So this takes vec, applies into it, and you get back vec of int. Now, of course, you could have written vec of int, but now you can do it programmatically. You can do this inside a concept function. You can start building up a bigger type out of vec of int. Right? One of the functions you could apply to that vec of int is one that's inside that meta header. It's called members of. Members of, if you give it a reflection of a class type, will give you all of the representation of all of the members in there. And it's really saying all the members, type ages, classes, enumerators, non-static data members, static data members, virtual functions, ordinary functions, split fields, everything. Right? And you can do things you want with them. There's a second argument, which wasn't there in the original proposal. This came fairly late. It tells members of what point of view should take for access. Some people want to be able to see everything in class. Some people really don't want you to see everything in class. Keep things private. So there's a requirement to pass in an access view, and you can audit that in your source code. Now, of course, you can write your own const-eval functions. Right? Reflection landed today, but we've been working on it for a long time. The const-eval feature, I'm not sure how many people here are familiar with const-eval functions in C++. Okay, most. So const-eval is like const-expr, except it only exists at compile time. That feature was put in the language specifically for reflection. We knew we wanted to land here, so 8 years, about 8 years ago, maybe 6 years ago, I'm not sure. We worked on inserting that already ahead of time so that we had all the machinery needed for reflection. So you can write your own functions. You can do all kinds of interesting magic now that they have the reflection tools. And one final observation is that you can use reflection values as template arguments themselves. So it's a valid template argument, and it's incredibly powerful. I might use that a little bit later in a slide, depending on how I will do this time. All right, so the final bit that we need is that we compute our reflective information, we synthesize your reflective information, and eventually you want to turn it back into a bit of source. Right? So there's an inverse of our reflection operator, is what we call the splice operation, splice construct. It's a new set of tokens, delimiter tokens, so square bracket colon, on both sides of the expression. So the expression can be anything that computes an info, or you compute something convertible to an info. And so this particular line here is equivalent to saying int x equals 42. You never write it this way, of course. But maybe you have a variable that you want to declare with a computed type. Very easy to do. Right? You have to sometimes tell the compiler, this is a template, you have to tell them, I know you could either have an expression or a type in this context, it's a type. And so you will prefix it with type name. The rules are the same as for templates. Same with template. In order to know that this is a less than, you may have to say template with splice before you can say that before you specify some template arguments. You can put a qualifier after it, and the compiler is smart enough to then know that whatever comes before it is a namespace, an enum, a class, or something like that. Right? And of course, you can just splice values in expressions. So that's P296 in a slide. I'm not expecting you to now be experts on it, but I did want to put that background a little bit so we can go over some examples. All right, here's a sort of warm-up example. I'm going to define a very simple class called entry. Right? I gave it a few non-static data members, and I chose some bit fields because a lot of reflection systems that have been proposed before have a hard time dealing with bit fields, but we have, for us, it works just fine. Okay, so let's get a handle to what the compiler's understanding is of entry. So I'm using my reflection operator on entry, and now I have that value. I can do all kinds of meta functions on it, but one simple one is just ask, what's your name, right? If you want to write a function, for example, that turns enumerations into strings, you would use identifier of on the enumerators of that enum. It's one of the many requested features of Clang. Sorry, not Clang, reflection. More interestingly, perhaps, I can ask for the non-static data members of R. Right? So I will get 3 elements as a vector. I can index it, I can use any standard library algorithm on that. In this case, it's a very simple example, so I'm just taking element 1, which, we start with 0, so 1 is key. And I can ask to print out the name of that key, so that should be key. But I can also just access the actual key, right? So I can use a splicer wherever I would have used a regular entity in the past. I can instead use a splicer. Right? And I have demos for most of these things, but I probably don't have the time to go over all of it. Let's see here, let's go full screen. Can you guys read what's up there? So you see, it's doing what we wanted, right? It prints out entry, key, 100. If I were to change that to, I don't know, to take number 0 instead, I would expect flags here, yeah. And XD is 13, so that's good. What if I introduce an alias? By the way, one of contributors to this is Peter Dimov, who is one of your contributors. I don't know if he's here. Are you here, Peter? Oh, hi, Peter. Thanks for all the work. So we can do something like this. And there it goes. So it updates Peter. So you can dynamically explore, not dynamically, as compile, explore your whole program. So that's just a sheet in action. So how can reflection regularize C++? Well, the first thing it can do is, as I mentioned, represent the language in a simple way. So we'll look at some examples. There we go. So imagine a struct. What's actually a class member? Well, int I is clearly a class member. It's a non-static data member. Fine. What about in J, which is very similar, but it's a bit field? Is that still a class member? Yes, the language says that's still a class member. That's good. Well, I need a gap between my bit fields, so I can actually specify that I can insert an unnamed bit fields. The language says this is no longer a data member. Right? But for reflection, that'd be painful if we needed a different thing to represent a gap in a bit field. So instead, from a reflection point of view, it still is a data member. Right? Sorry, it's still a class member. It's not a data member because we don't want to accidentally write in it. But if I ask for the members of this class, right? I'm going to write a little function to count the fields of the class. Right? So I go over all the members, and will at one point become a representation of this unnamed bit field. And so I say, okay, if you're a non-static data member or if you're a bit field, so these two are bit fields, but only this one is a non-static data member. So J is both a non-static data member and a bit field. This unnamed thing is only a bit field. I is only a non-static data member. So I count them, and I would expect that if I apply n fields off to the reflection of S1, I should have 3. Right? Pretty straightforward, but that is a small decision we made in the design of reflection to regularize the language so that you don't have to have a whole new notion just to represent unnamed bit fields. We still have non-static data members off that will not represent that because you don't want to, if you do for all your members to write to them, you wouldn't want to write into blank space. Here's another similar case, sort of the opposite in a way. The language actually says that A, B, and C are members of S2. That's very annoying. You don't want double ownership when you traverse your program. So reflection says A, B, and C belong to E only. They do not belong to S2. But we don't care about lookup. We care about structure. Right? So if I write a function that goes over all the members of a class, it should never hit is enumerator, right? The enumerator are the constants, not the type. That's called the enumeration type. Right? So class as enumerator will be false for S2, but exactly will be false for any class from the reflection perspective. But you can of course ask the enumerator itself, you know, what are your elements? So you get a vector back of reflections for A, B, and C. In this case, I'm just asking for the size, I will get 3. Does that make sense? If at some point something is really unclear, feel free to interrupt me. Here's another one that's always annoyed me in language. Everyone familiar with anonymous unions? Yeah, it's looking good. So, according to the language, S3 has 3 members, C, I, and F. According to the language, there is no union type in this example. This notation union there is not really union type, right? But that's not how implementers implement it. What they really say is there's 2 members in S3. There's C, and there's an unnamed member that holds the other members, right? And so that's how we're representing it in reflection. We regularize the representation. If you ask for, this is one of the functions that we have, for the parent of C, well, it will be S3. But if you ask for the parent of I, it won't be S3. The parent of I is a union type. Right? What's more, since I can ask for the parent of I to get that union type, I can splice it in. So this is something you couldn't do before in C++. You can grab an anonymous union type and you can make a variable of it. Could be useful to make a copy of the variant numbers, for example. Right? This is a type I can use designated initializers on them. And finally, I can ask non-static data members of S3, how many members does it really have? And it will say 2, right? That's C and that unnamed member. Right? So those are just a few examples in how we simplified the language model. So the other thing we did that also regularizes thing, as I mentioned, is we have a homogeneous value to represent everything. That allows us in the future to adapt, right? We don't have to think about how we're going to represent future features in the C++. We already know it's got to be info. Now, you know that we have different kinds of template arguments, right? Like type name and so on. Like we have templates. C++6 actually adds a couple of different templates to this list, right? And so you can say X float 42 instead of array. But now you need to know ahead of time which kinds you're going to expect. Also, if you want to pass a namespace by template argument, you're out of luck. You need to go to the committee and present a feature for that. Whereas reflection, we get it for free. Right? I can just say template auto ... and now I can pass whatever I want to my template. Right? You can pass in namespaces, you can pass in base class relationships, you can pass in your own representation of a data structure, all kinds of things you can pass in. Right? So I can pass in float, I can still pass in 42, it's still a value. I can pass in array, I can pass in MSVC. So it shows you the power of making things more regular, more uniform. All right. Now we're going to look, how am I doing on time? Let me just check here. So good. Okay, thank you. We're going to develop a tuple type that's like standard type. Now, how many people are familiar with tuple? Yeah, most people's programs stand tuples. How many of you have looked at the implementation of tuple in your header files? A good number of them. Wasn't easy, was it? Like hundreds of lines of code. Have you ever blamed your compile times on std variant? Std variant is similar, std variant is similar to tuple. Turns out that with reflection we can implement these things a lot more briefly, a lot more directly. Someone on Reddit a few weeks ago used the prototype implementation of Clang to implement variant using reflection, and he said it compiles about 20 times faster. So anyway, we're going to see how we can do it in tuple. Now these slides are a little outdated. I copied them from our presentation, so it's not completely up to date with what has been accepted today in the language, but it's very similar. You can do it. You just have to change a few. Like this function define class is now called define instead. So what are we doing? tuple no longer derives from anything, no longer uses recursive templates. We're just going to define a class storage that's going to hold all our members of the tuple. But I'm not going to write them out, I'm going to programmatically add those members. Right? So I leave storage undefined. And then there's a new feature called a concept file block. You could put a static assert, you can say concept file open brace, and you can put some code in there, and that code will be executed as a compiler processes that block, right? As if it was static assert. So I'm going to say, okay, now go ahead and define the storage, and I'm going to give you a range of descriptions of data members, right? There's a function called data member spec that creates a description. And I give it a reflection of TS, and I'm going to pack expand that. So this is actually multiple calls to data member spec, and I'm stamping out a description for every member that I want. So you give it a type and you give it a bunch of options. One of the options is names, so I could give them names. I could give them a bit field width if I wanted, or an alignment. But the only thing I'm interested in, I wanted to have the no unique address property, so that if that's compact as a standard solution. You do that, and that's a close sync brace as a concept file. That's very ugly, but I need to fit it on the slide. And boom, storage now has a member for every TS in my pack. I'm done. Right. Way easier and way more efficient than what we used to do in C++. So now I declare my member data, and I can go ahead start to implement my tuple type. Right? For example, my constructor can just do an aggregate initialization of my parameters that came in. Right? One liner, and you're done. And it's fairly easy to read once you work with this for the other. I understand that presenting you with the syntax today is probably like, oh, there's a lot of braces, parentheses, and dots, right? If you have tuple, one of the key protocol parts of tuple is tuple elements. So I need to specialize this for my tuple, right? And I'm going to use reflection to implement that. So how do I do it? I pack expand the reflection of my template arguments, right, into a stud array. So this is a stud array cast of a list of reflections. And now I can index them. Right, so in one expression, I've gotten the reflection for the eyes template parameter, but I need actually not the reflection, but the actual type, so I can just splice it. Now, turns out that in C++26 you don't need this. In C++26 I could replace this whole thing by just TS like that. That's even nicer, right? That's very direct, but it's very ad hoc. It only does that, right? I think if we had been sure that we're going to have reflection, we might not have added that one very specific feature, because this is pretty good. It's not as compact as that, but it turns out that once you have compile time reflection, you need this a lot less, because this array, instead of doing an indexing right here, I probably want to pass it down to an algorithm that's going to do all kinds of things. I can pass that array to the standard library function. If I want to sort that array, I can do that now. If I want to duplicate it or deduplicate it or whatever I want to do, this only works using template association. You still have to do a lot of complicated template metaprogramming if you work with indexing. Right? So this is one of those ad hoc features where I think reflection gives us a universal solution that is more pleasant to work with at scale. You also need a get function. So I wrote a quick function that gives me the nth non-static data member of my tuple, right? It just asks for the non-static data members of my storage and indexes it. Right? And then my get function, there's several get functions, I'm just showing one because you need one for ref, for const ref, and so on. Right? But it's again a one-liner, right? Let's say t.data and then t.ends nsdm and then pass that I in there. And I'm done. I'm not going to show the demo on Compiler Explorer because I prefer to have more space for questions. But if you go back to our list, remember I said all these things that we would like for tomorrow. For all these things that reflection helps in regularization. I think just this tuple example shows you how, we used values for non-value concepts and could handle everything uniformly. We didn't have to worry about, well, there's different kinds of types in our tuple. No, just they're all inflows. Right? Like member access, right, became a uniform thing. That you don't have to worry about a different syntax for each access to a member. You can just have one that accesses any member. We didn't need that additional feature of back indexing. It just comes out of it. Let's see. Here's another example. Another time. I mentioned we can look at pointers and references the same way, right? So you know the size of operator without an underscore. If you apply it to a reference, you're not going to get the size that the reference occupies in your memory. Instead, you're getting the size of the thing underneath it. It can be confusing. But here, the size of, in the reflection, the size of a pointer and the size of a reference are equal, and the language now specifies that, right? You can ask for the offset of a pointer, but you can also ask for the offset of a reference. So you can actually explore structures that contain references as well as structures that contain pointers. Right? Same for alignment. Here is one that I love. It's from Barry Revson. We've already seen that we can go through the data members of a structure, of a class, any struct class. But what about base classes? You can ask for the basis of a structure. In this case, I have a structure with D that has an ambiguous base class in it. So B is inherited directly and indirectly through C. Currently in C++, there's almost no way to get to this B. You need to work through something, a function like this, get that in your intermediate class. But with reflection you can. So when I ask for the basis of D, I get the immediate ones. If you want a non-immediate one, you can recurse. Right? But I only get I'll get two elements here. I'll get B and C. And then I can actually, so how do I get to the base class? Well, in regular C++, members are accessed through the dot notation, and basis you have to cast. But why not the dot notation for your members? Well, there is an ambiguity if you try to use type syntax. But with reflection, there's no ambiguity. I can just say D dot a base class reflection, and now I have gotten to this B. Right? So there's a regularization of an existing mechanic. Right? There's a mechanism in C++ to access sub-objects. There's actually two. There's the data members and the base classes. But what we have done is we have made one work for both. So if I add 10 to B of B, it's 10 to this direct base. The indirect one here is unaffected. Right? So it was, I initialized it to 1 here. The other one is 0, so this is default initialized. Right? So that is now 11. If I multiply it by 10, I get 110. Now we have a function called subobject_of, which will give you both the basis and the non-static data members. And so with a single loop, and there's a new construct that allows you to stamp out code, template 4. With a single loop and a single expression, you can access any of the direct subobjects of your class. And you can hash them, serialize them, do whatever you need to do with the subobjects. This is a separate paper, but it also got accepted today. There's about a half dozen papers that got accepted today. All right, that's how far I want to go today. Just show you that reflection is going to allow you to do a lot of new things, but mostly it's going to simplify your language. It's going to simplify the view that programmers have of the language, and will, through that, keep under control the algorithms and the new directions we're going to go to. I'm open to any questions. Thank you again for inviting me, and I'm very excited about what we'll be able to evolve with that.